So, okay, in case you were wondering about my accent, it's because I'm from Greece. And the reason I'm here is because in Greece, we invented the wind. We actually did. We invented wind. If you've seen the movie My Big Fat Greek Wedding, you probably know about this already. So Aeolus was the god of winds, the keeper of the winds. And not only did we invent wind, but we invented the first wind turbine. 1st century AD by Hieron's wind wheel. And yours truly here has been trained by the best wind engineers in Greece as an undergraduate. And my diploma thesis was based on state-of-the-art equipment such as this. So whatever I say here is really state-of-the-art about wind today. But let's stop the jokes and go on with the presentation. So I will talk a little bit about this Vienna rectifier, the basics. And then I will discuss two topologies. The first one is a Vienna rectifier with an induction generator. And the second one is with a permanent magnet generator. Okay? Is it working, Sid?
It looks like it.
Looks like it.
I'm not seeing the broadcast.
And I will conclude the presentation with some discussion of a new PhD program we are establishing at Iowa State University called Wind Energy Science, Engineering and Policy, or WESEP for short, because Dr. Sid asked me to talk about this a little bit. So let's see. So the Vienna rectifier is a power electronics topology that looks like this. Okay, so it's also called a three-phase, three-switch, three-level rectifier. So why is that? Because it takes three phases as an input, A, B, and C, and it gives you DC output, so it rectifies. And it's called three-switch because it has 1, 2, 3 semiconductor, controllable semiconductor switches like IGBTs, for example, instead of the usual type of bridge that has 6. The typical three-phase bridge has six controllable devices. And it can give you 3 levels of voltage output. What that means is from each phase to this neutral point there in the DC link, you get 3 levels. And I will explain how that works. So what's this now? Let's get rid of this thing. Let's see if my graphics work. Okay, so to get a quick understanding of how this thing works, let's say the current coming out of this phase from the input here, from the AC input, is positive. So it goes in like that, like the red line. And let's say at that time I decide to switch this one on. So at that time the current is going to go up this diode, down this switch, up the other diode, and then end up at that point. So what I'm basically doing is I'm able to connect this point, essentially through all these semiconductors, to that point. So the voltage from A to N is 0. Okay? If, on the other phase, let's look at the B phase now. Let's say the current is positive again in that phase. But let's say I decide to turn the switch off. Now, what happens if you turn the switch off, the current will follow a different path. It will go up this diode and end up there. So the voltage then that you get between B and point N is basically the voltage of this capacitor. So it's half your DC link voltage. And when you have negative current, which is what should happen in the third phase because the 3 currents need to add to 0, okay, this works better, I suppose. What happens is you can do the same analysis, but in this case I didn't turn the switch on, I let it be off. So the current now is coming from the bottom, so the voltage from C to neutral is minus half the DC link voltage. So what I'm trying to tell you here is that from any of these points to this neutral point, the voltage can be either 0 or plus and minus half the DC link voltage, according also to what the current is doing. Is it positive or negative? So that's why it's called the 3-level rectifier. Okay? And this topology was invented in the early 90s by a professor called, what's his first name? Johann, I think, Golar, probably in Vienna, most probably. That's why it has this name, the Vienna rectifier. And it his grandmother maybe was from Greece. So the primary application of this invention at that time was to be used to rectify AC voltage to be used in telecommunications applications or UPS. The reason is it turns out you can make this a really compact topology, so you can have higher power density than with a traditional, let's say, 6-switch inverter. And you can also get sinusoidal input currents with very good THD. Because you have these, you can get more voltage levels out of this than from a traditional 6-switch H-bridge inverter. And you can basically tell, if you're a little bit familiar with power electronics, that this can only work in one direction of power flow. It is only a rectifier. It cannot take power from the DC side and shoot it back to the left. So we have to keep this in mind. It has only 3 active switches instead of 6. And so the control, designing the control circuit is a little bit easier. You only need 3 gate drives. Another advantage is that in case of a control failure, the DC link doesn't short circuit. And for us, for our application, it's really important to note that there is reduced stress, voltage stress on the semiconductors. It's actually half the DC link voltage instead of the entire DC link voltage. So as we will see later on from some of our results, this reduces the switching loss of these semiconductors. Okay, so it leads to a higher efficiency, which is important when you're talking about a generator application. Okay, and it can also lead to reduced switching loss. That's what I basically just said. So let me talk a little bit about how you generate the voltage. How many of you are familiar with this kind of diagram? I don't want to confuse you that much. This is a diagram that's called the space vector, voltage space vector diagram of an inverter. And basically what this shows you is the different types of voltage that you can get as points on this space, depending on what switch you turn on and off. So you have 3 switches, and each one can give you, let's say, 3 different voltages. So 3 times 3 times 3 gives you how many? 27. Actually, this inverter can give you 25, but I don't want to go into that detail. But all these points are put here. So from an inverter, basically, you get discrete points, depending on how you switch the switches on and off. So what happens is, in simple words, is that by averaging the voltage, the discrete voltage that comes out of the 3 switches in time, you can get any voltage on this plane, basically, or inside this hexagon. So, for example, if you want a voltage to be inside this,
Sorry to interrupt, Dionysios. We can fix this if you don't mind right away.
I don't mind. Go ahead.
And Jeff wants to make sure that the microphone that you have is turned on. If you could do that. Looks like it is. So tell me what to do. Correct? Yes. Yeah, I do. No, I don't think it's bringing up anything. Oh, hang on just a second. Should I say share on that? Oh, this is not on the speaker's computer, but on the other one? I'm on the speaker's computer here. Perhaps I'll just wait for you to come. How about that? Okay, so I'll just let our speaker continue. Sorry about this.
Should I continue?
Yeah, please do.
So I'm trying to explain to you how inverters work in one slide, but it's kind of impossible. But the idea is that you can get any voltage here by appropriately switching the things on and off, deciding which ones to switch and how long to keep them on. So you take, let's say, 30% of this point and 40% of that point and another 30% of that point gives you some kind of average voltage inside that triangle, okay? So whatever the average, whatever the voltages you want to get on an average basis, you determine which ones to turn on and how long to keep them on, and you can get that voltage on average. And then, of course, because this is an AC voltage, the voltage basically rotates around like this all the time. So you switch, you use different switchings as the voltage moves around. So what happens is that as the voltage, it turns out for this type of topology that depending on where the current now is, so this is the red one is the current, depending on where that current is, you can only use a subset of these points. Okay? Yes, please go ahead. So it turns out this. Now, this topology has a special characteristic that the voltages that you can get depend on where your current is. So this red one is the current. So this vector. So if that vector, for example, is from minus 90 degrees to minus 30 degrees, so in that range, you can only use this pink hexagon of points. If the vector, as it rotates, it passes the minus 30 degree and is anywhere in between minus 30 and plus 30 degrees, so in this range, you can only use this, what is it, yellow hexagon. Okay? So you switch hexagons. It has 6 hexagons that you can use as you go around. So the key is that look at what the current is doing when it is at exactly minus 30 degrees, for example. So at the moment, the current is switching from one hexagon to the next. Okay? What happens is that at that point, if you want your transition to be smooth for the voltage, you can only generate a voltage vector that is actually inside at the intersection of these 2 hexagons, which is this green parallelogram. Just believe me, that's true. So basically what this is telling you is that the voltage can only deviate from the current how many degrees? Plus minus 30 degrees. Okay? So that gives you a constraint. In electrical engineering, we call this a constraint on the power factor angle of this topology. It also, apart from the angle, you cannot be outside this, little parallelogram. It also gives you a constraint on the magnitude of the voltage. So if, for example, you're at this angle here, beta, the maximum voltage that you can get out of this thing lies on this straight line there. Okay? So you have 2 constraints. And so mathematically, the first one is that beta needs to be between plus minus 30 degrees. And the Vmax, there is a relationship for Vmax. Can you see that? There is better. That depends on the cosine of beta. Okay? So let's keep these things in mind, because it will affect the operation of this topology. So now let's go some basics about wind that I'm sure all of you are aware of. So when you have a wind turbine, or a well-designed wind turbine, what you really want to do is increase the power that you generate with respect to wind speed, basically cubic, following a cubic trajectory, v to the cube. That's what you really want to do. Up to this rated speed. Okay, so you start here, you end here, and then you try to keep rated power. So it turns out that this wind speed in a wind turbine is actually proportional to the rotor speed of the generator. Okay, you keep that proportional. So how fast your generator spins is proportional to how fast the wind blows. So for the analysis that I will show you, we will assume that we are doing this thing so that our speed of the generator changes proportionally to wind speed, and we will assume that we're in some kind of electrical steady state. And why is that? Because typically large wind turbines have a lot of inertia, so as the wind speed changes, you're basically always in some kind of, electrically speaking, in some steady state. You just move around slowly, following basically the change of speed of the blades and the rotor, which has a big inertia, so it does not accelerate and decelerate very, very fast. The time scales are different. So the analysis will be on a steady state basis. So the first topology that we analyzed, for some reason that I'm not exactly why, because nobody uses squirrel cage generators in wind turbines anymore, but we said, okay, let's just try this, is to use the Vienna rectifier with a squirrel cage generator. So this would be your wind turbine. The blades are out here, driving your generator, and the power flows out of the rectifier onto the DC bus. And here you can have, for example, a DC to AC topology, which is not shown, going to the grid. So what happens now is that this induction generator, if you took the undergraduate course in electrical engineering, it turns out that this absorbs a lot of reactive power. Okay, so that means that if you just connected this with the induction generator, it would not work, because you would be violating that angle constraint that I was talking about previously. That beta, or the difference between the voltage and the current, would be much more than 30 degrees. So it turns out that you need to connect some kind of capacitance here to supply the reactive power of this turbine. And so by putting this LC filter, everything works out okay. But I don't really want to go into the details of this analysis, because it might take us another hour. So the idea is this. Like we said, the power is proportional to the cube of the rotor speed, which means that the torque that you need to generate is proportional to the square of the rotor speed, which means now that if you do vector control of this machine, using this one to control it, and if you're familiar at all with how machines are controlled, basically there's two components for the current, one in the Q-axis and one in the D-axis. Basically it means that the Q-axis component of the current is proportional to the torque, so it's proportional to the speed of the machine squared, whereas the other component is constant. And then also the slip frequency of the machine will be proportional to the speed squared. So why is this popping up? Okay, so with this in mind, if you think about an induction motor that you learned in high school, maybe, this has an equivalent circuit. The equivalent circuit, you can solve the equivalent circuit, it turns out, for any wind speed that you have, because if I give you the wind speed, you know how much power you're supposed to produce at that wind speed. You know at what speed you're supposed to produce that wind power. And so you know everything there is to know about this equivalent circuit. You know the slip and all those things. And so you can solve it. So it turns out we can solve for a range of wind speeds what happens in this case. So basically, in one slide, what happens is this, that this thing can operate from a range of wind speeds. So it can actually be a variable wind turbine, variable speed wind turbine. But the range of speeds that you can get depends on the capacitance that you select for that filter. So for example, if I select some value of capacitance here, I can go maybe from 55% per unit to almost 1 per unit wind speed. So if I choose a different value of capacitance for my capacitive bank, I am limited. So I'm always limited by these two curves, is what I'm telling you, which are basically the 30 degree, plus minus 30 degree angle constraint of the Vienna rectifier. So the idea that we implemented is to, okay, if you really want to go from a very low wind speed to nominal, so that you can extract maybe a lot of energy from your wind turbine, you have to find a way to switch from, using different capacitance levels. So you can have a switched capacitor bank if you would like to do it like this. All right? Now, here's a tricky point. Since this topology is unidirectional, I told you before that power can only go that way. The question that you might ask me, okay, how do I charge these capacitors in the first place? So these capacitors need to be charged initially before this thing starts operating. So since I cannot bring power from here to charge them, how do I do that? So it turns out there is a magical phenomenon in induction machines, which very few people understand, which is called self-excitation. So there is a soft spot there, if you want, that if you put the right capacitance there with the right machine and you start spinning it, you will see the voltage there build up automatically. It will self-excite. Okay? And we took advantage of this in this topology. And it turns out, magically again, that the capacitance that you need to self-excite is outside the range. So the machine will self-excite before you even start operating it. So that's a good thing. So it works out nicely, like that. And let's see. These are plots of the voltages and the currents on the machine terminals and the generator terminals. The interesting thing here is if you look at the Vienna rectifier versus what happens at the generator, the current that flows in the Vienna rectifier, which is this dashed line, is what? Compared to this current that is flowing in the machine. It is lower. So that means that the conduction loss of this topology, because it has lower current than what you would need if you connected directly to its terminals, will be lower, which is also another good thing. So here's some loss comparison that we ran. This was done by comparing the proposed Vienna rectifier topology with a traditional, let's say, 6-switch IGBT-based inverter, which is what is most often used in these types of applications. So here I'm showing the switching loss. So the semiconductors basically have two types of loss. The switching loss, which occurs whenever you turn them on and off, and the conduction loss, which happens when you have current flowing through them. So the switching loss, when you look at switching loss, the dark black bars here are for the 6-switch IGBT-based inverter, and the other ones are for the Vienna. And which one has less? The Vienna has less. It's a better, more efficient topology. Now, when you go to conduction loss, it turns out that Vienna is not doing very well. The reason for that is because you have these diodes, you have more diodes, and you have current flowing through the diodes. So when current flows through the diodes, you have some kind of conduction loss. But if you look at the total loss, if you add these two things together, the total loss actually turns out that the Vienna outperforms the 6-switch traditional bridge. Okay? So typically in a wind turbine, you might actually, you don't always operate here and you don't always operate there. Depending on how the wind blows, there is a probability that you will be here and here and here and here. So if you weigh that properly, according to the statistics of the wind, you can do a total, let's say, energy output. You can forecast the energy yield out of that thing. And with this comparison here, we basically found out that using the parameters that we use, that using Vienna rectifier, you can have about 1% more basically annual energy yield out of the same turbine. So 1% might not seem too much, but it is a lot if you think about it. If the technology is mature, for a mature technology like these kinds of things, getting a 1 or 2% increase in the output is actually a very good thing. Okay? It means basically more money to the wind turbine owner. Okay. Any questions so far? Go ahead. Can I take questions now, or do I have to wait?
But student might need microphone.
Oh.
And then they have to turn it on, push it all the way up.
Is it working?
So the diagram which you showed where you had the current and the voltage, the dip, I think 2 slides before. So you had a reactive power compensation technique. So I didn't understand why was there a voltage dip as well? Because if there is both voltage and current dip, that means there is a greater loss.
Do you mean at these points?
No,
these
I mean,
dips?
Are those,
So the question is, what happens here and the voltage dips?
Yeah, why is there a voltage dip though you used a suitable
So
capacitor?
this black line is the voltage of the machine.
Right.
Okay? So since this thing is operating at low speed, because it's a variable speed machine, that's the voltage it needs to give you that amount of power at that speed.
Right, yeah, so I'm saying this is measured at the generator's terminals,
Yes.
and the other one is at the rectifier terminals.
Yes.
There's a dip from generator terminals to the, as compared to the rectifier terminals, if I'm not wrong.
So this black line and that solid line are not exactly the same. What do you mean by dip?
Yeah, exactly, that's what I mean.
So they're not exactly the same because in between you have something. You have an inductor, basically you have an inductor and the capacitors. So the voltage here is not exactly the same as here. They're kind of close actually. Basically you only have the drop on this inductance. But the current is dramatically different because these capacitors inject a lot of current which doesn't need to flow here. So you're saving some reactive current here, you're making this thing more efficient if you were to use an induction machine like this. Did I answer your question? Any other questions? I will move on to the other one, which is kind of more interesting because it uses a permanent magnet generator, which is more typically used in wind turbines. And before I do that, I'll show you the experimental results, which are interesting for the induction generator. So what I want to draw your attention to here, compare this current with that current. This current is the current that the Vienna rectifier gives you at the terminals, this current here. This current is what the machine absorbs. What's the difference between the two? Is that this current has a lot more harmonics, and because of the presence of that filter that we have to put there to compensate the reactive power, you get a much cleaner current for the machine, which basically means that the torque that you're going to get out of this turbine will be very, very good quality torque. This current will give you a torque that will have a lot of noise. And I'm not a mechanical engineer, but this might have something to do with the drivetrain of wind turbines and reliability issues and stuff like that. So it's good to have this type of current and not this type of current from a variable frequency basically drives. So this is one of the advantages. The other thing I would like to draw your attention to is the waveform here of the voltage, where basically you can see the different levels of voltage that you get out of the Vienna rectifier. And I apologize for this spike. This is due to switching effects that we couldn't eliminate in our prototype. Our prototype was not perfect. We only did this with a small machine and with the means that we had to demonstrate that this thing works. But you can clearly see that this, actually the output of the voltage here, you get more levels out of what you would get from a traditional 6-switch inverter and gives you better quality, even better quality for your currents. So now let's go to the permanent magnet machine. So the idea here is, this is what type of machine, how do we call those? Type 4, okay, type 4 turbines. That uses a permanent magnet, here your blades, gearbox. Not necessary to have a gearbox. If it's direct drive, you get rid of the gearbox. And what you do now is you have AC to DC, DC link, DC to AC transformer, and goes to AC grid. Or to the collection. This could be collection system of a wind power plant, and then grid. So the idea is take out this component, which is, this is the 6-switch converter that I've been talking about so far, and replace it with the Vienna. Everything else stays the same. I cannot use a Vienna here. Why not? Because this is unidirectional, so I would have to be, drawing power like that, which is not what I want to do. So I can only replace the generator side converter. So now let me explain this to you now. If we were to use a 6-switch rectifier, the traditional way, this is what happens when you use a traditional way. What this plot has currents on the axis. This is the D-axis current, and this is the Q-axis current of the machine. There are certain limitations when you drive a PMSG, a permanent magnet machine. The first limitation is that your current magnitude should be limited by a maximum value. That translates to an equation like IQ squared plus ID squared less than some number, which basically gives you what type of line? It gives you a circle. Here's that circle. Half circle. So this is the current limit of this topology. And then the other limit comes from the voltage. So as the wind turbine speeds up, as the wind blows harder and harder, you need more and more voltage to drive the currents into that machine. And so at some speed, you have a voltage limit, which is basically, this line is part of a larger ellipse, which is like some huge ellipse here on this plane, which I'm not showing. And as the speed increases, this ellipse shrinks and shrinks and shrinks. So this is a voltage limit at one speed. This is another voltage limit at another speed. So for a wind turbine, what we do is, for any given speed, give me a wind speed. I can find the rotor speed that I want and the torque that I want. So this line here gives me the torque that I want this thing to give me for a given wind speed. And this other line here is the torque for a higher wind speed. So to get this torque, what this plot tells me is that I can use any combination of IQ and ID that are on this line, limited by point A, which is on the current limit, and another point here, B, which is on the other side of the current limit. Okay, so I'm limited by current for low wind speeds. For higher wind speeds, because this ellipse shrinks, I'm now limited by C here, which is a voltage limit, and by D on the other side, which is a current limit. So the idea is that we can plot a lot of these curves and do this analysis and figure out our limits for any wind speed. And so you get a plot that looks like that. So this is the feasible operating range of such a turbine. So, for example, for this minimum torque, I can get this minimum torque if I put any combination of IQ and ID currents on this line. For this torque, for that torque, I can do like that. Of course, which one do I choose? Which combination of currents will I choose? This one, or that one, or that one, or which one do I choose to drive my machine? So what they do is they try to use the combination of currents, or the current, that will give you the most efficient operation. Okay, so this is called, in PMSG drives, maximum torque per ampere strategy. You get the maximum torque for a given value of current to reduce your losses in the machine. Okay, now let's see what happens now when you have the Vienna rectifier, because things here are more complicated. That's why I showed you the previous slide first, to get you into the spirit. The current limit is still here, the same current limit. It's still a circle. Where is this circle? Is this here? It just shifted around. The axis, the zero, the origin has shifted. And now we have two more types of limits. We have the voltage limit, and we have a limit because of what was the other constraint we had from the Vienna rectifier? We had the power factor angle 30-degree limit. So these types of limits give you two different types of curves, which are no longer elliptical, like in the previous case. So they kind of look awkward. So let me show you what I have here. So the minus 30-degree limit and the 30-degree limit are these two lines here. You see, they start at that point and end there. Both of them actually have the same intersection with this axis, and there are these two curves out there. So if I am inside these two curves, anywhere inside these two curves, I'm okay. And the voltage limit now, which also depends on the power factor angle because of that second equation I gave you, has different shape now, which is, for example, this is a voltage limit for one wind speed, and that's another voltage limit for another wind speed. So you need to draw all these curves carefully on the plane and do the same process again. So for whatever torque you need to generate, you find the limiting points. For example, for this one, you are limited out here by the voltage limit, and here by the angle limit. Okay, and as you keep increasing the wind speed, you look carefully at your limits, and you come up with another feasible operating region, which has a different shape this time than before. Okay, so if you are inside this region, you are okay. So the question again is, in this type of drive, and we're actually the first ones that did this, I think, in the world. How do you select the current? What is the best way to select the current to give you the desired torque? So the constraint is you need to be inside here. I give you a torque. What current you will choose to get that torque? So we did an analysis, and the analysis was based on simulation. And we simulated this thing very, very carefully. We put in not only the generator losses, but also the losses from the power electronics, so as a system together. And we found which combination here. We did basically the efficiency analysis of this entire domain, very, very carefully in the computer. My graduate student did. I didn't do anything of that. And here's what happens. For the 6-switch, the traditional one, it turns out that if you do this maximum torque per ampere strategy, these are the points that you will follow to get your torque, okay, which is what people do today. For the Vienna rectifier, you have to do two things. So you start out here at low speed, low wind speed, low power, and you actually follow the MTPA as before. It turns out that this is the best way to do it. And as you go up, you're going to hit the voltage limit, unfortunately. And then you cannot keep going on the MTPA as you do here. And you need to switch from MTPA to another voltage limit curve. You're limited, unfortunately, by your voltage limit. But you can still get the torque all the way out to the maximum torque that you need. You can still operate the thing. You're just not going to be on the MTPA forever due to the limitations of the inverter. Have any questions so far? Are you with me? Keep in mind that the MTPA is derived analytically. So you write down, and derived analytically, and only by taking into account the equations of the generator. You write down the equations of your generator, your equivalent circuit, and you do like a 2-line proof that this is the best curve. The points that I show you here include the losses of the generator and the power electronics with complete detailed simulation, of the switchings and all those effects that you cannot do by hand. So interestingly enough, the theoretical MTPA curve that is derived by looking only at the efficiency of the generator actually gives you the best efficiency for both generator and electronics together, which for me it was kind of an interesting thing to observe here. So these dots that you see there are simulation results, so they are very, very close to that MTPA. Anyway, so let's look at the loss comparison again, like we did for the induction machine. So what do we have here? The triangles are the Vienna, the circles are the traditional one. So you see here that switching loss, Vienna wins. Conduction loss, Vienna loses, as before. But conduction loss is less than switching loss. So if you put the total semiconductor loss together, Vienna wins. And if you put now converter plus generator again together, Vienna wins again. Even though you deviate from your MTPA curve. So that works against you. Deviating from the MTPA curve due to the voltage limit is a bad thing. But even so, you win. Okay? You always have better efficiency. for any wind speed, basically. And so overall, your efficiency of the two systems, which is what this plot is showing, you can see clearly that the Vienna rectifier gives you at least 1 or 2% better efficiency for all operating points, or on the order of 1 to 2%. Okay? So for me, as an engineer, even though it doesn't look very impressive, it is impressive to me for a mature technology like this to be able to increase the efficiency of the process by 2%. To me, it means something. Because people try their entire lives for mature technologies to improve it even, 0.1%, 0.2%. These are incremental, but over the length of time that this thing will operate, over 20 years, they will make a difference. So here's an energy comparison now, not power, energy. So again, you see for this 1.5 virtual generator that we kind of devised, that you get about 1% more energy every year just by switching from the traditional converter to a Vienna rectifier. So you get about 1% more energy. How much money is that? Well, let's see. About 50 more megawatt hours per year. How much do they sell the megawatt hour to the system, the wind producers? $50? Okay, so 50 times $50. How much is that? $2,500? So that basically pays off like the rent that you pay. In Iowa, we pay the wind turbine owners pay rent to the people because underneath there is farms. So you pay some rent to use the farmer's land. That basically pays off the rent, or part of the rent, because I think the rent is on the order of a few $1,000s every year. So it's not millions of dollars, but it's something that gives you some extra money. So that means designing your system in a smarter way. And this is the experimental prototype we built in the lab. So where's our wind turbine? Here it is. It's very small, okay? The prototype was a fractional horsepower kind of thing. But it doesn't matter because the machines, they work the same even if they're 1.5 megawatt. The equations are the same. What we wanted to show here is that this thing works, so the proof of concept. And we cannot build a 1.5 megawatt turbine in the lab, of course. That's for GE to do or Vestas. And these are the experimental results that we got. The currents. The noise here, again, unavoidable due to our prototype. But you can clearly see the levels, the voltage levels that you get out of the Vienna rectifier in the current waveforms. So for high powers, actually here, there's two ways to operate this. One way is to do space vector modulation, like what I'm doing, which doesn't guarantee that you're going to get completely sinusoidal current. Or you can switch to hysteresis type of control, which will then guarantee that you will get a completely sinusoidal current. Okay? So you can do that as well. So I'm done with the Vienna rectifier part. Do you have any questions about this technical part of the presentation? Yes, sir.
So a lot of the commercial IGBTs have a flyback diode already built into the IGBT
Module, yeah.
So in your case, were you using IGBTs with separate flyback?
I think in our prototype, because that's the thing you can buy, we were using it, but the topology itself, I think, never uses that diode. It's never used.
Okay. So you were essentially doing with discrete diodes around your...
Yes, the other diodes, actually, that's a good point. What are all the other diodes? Let's go back to that. Maybe, I don't know how to use this very quickly, but let me see if I can do it from here. There's a lot of diodes in that circuit, so let me show you. Okay, these diodes here, let's see which ones. As you switch this thing on and off, fast at the kilohertz range, you see that the current goes from here to some other diode. But this diode always carries the same current. Even if you switch this, the current is going to go like this or like that, like this or like that. So what you need to do is use common diodes for these ones because they don't switch very fast. For these ones, you need to use some kind of fast diodes, like Schottky diodes, that have, you know, quick recovery time. So you use a combination of diodes. Yes?
I'm trying to be loud, but if you can repeat my question, that would be great for people that are coming.
Oh, yes, I will do that.
Okay. See, I had to step out of the room, so maybe you already addressed this. The Vienna rectifier, as I read it, doesn't have a connection to the new the three-phase three wire system, correct? So how do faults? How do you handle faults in the system?
Fault where? Like in what part of the system?
On the generation side of the system.
So you would have to have a separate ground. The other 6-switch inverter doesn't have a ground either. These things are floating. The power electronics are always floating with respect to ground.
So if you give it a positive, then you can have voltage right through this system.
What do you mean by that now? You're opening a different subject.
Yeah.
Do you mean a fault happens in the power system?
Well, a nearby fault on the system, and you're trying to feed the fault current using your wind turbine right now. Two topics, actually.
You know, let me clarify something here. And maybe the other picture is better. If a fault happens here, this whole thing needs to collaborate together to handle it, and sometimes you put something on the DC link to dissipate the extra power coming from the wind turbine. So the analysis here is only steady state. We have not had a chance to look at how to deal with faults in the system and so on. We are the first ones that actually did this.
But is there a plan for you to look at that?
Yeah.
Use the mic.
It doesn't really work well, Sid.
Can you please go to the slide 20 where there is conduction losses for Vienna and the conventional?
Slide 20. Use this one. This one. Next one. The one. This one.
The losses, yeah. So in the Vienna rectifier we have 3 switching devices.
Yes.
And for the conventional we have 6 switching devices. So I'm not convinced why the conduction losses of how the conduction losses of 3 switching devices could be more than 6 switching devices.
So that's a good question, but this is the conduction loss together with the diodes.
Oh, because we have
All the semiconductors with the entire rectifier conduction loss. So you have three IGBTs, which probably give you less conduction loss on the 6, but you have now more diodes, and there are actually 2 of them connected in series, so you lose in terms of conduction loss. However, the other advantage of this is I'm going back again to this reduced voltage stress. You get half the DC link stress across the semiconductors. We think that this will lead to increased reliability of the system. You don't stress them to, let's say, 1,000 volts. You only stress them to 500 volts. And we have seen a few papers that kind of hint to that effect, that you increase the thermal stress on the device is less, which leads to increased lifetime and increased reliability as a consequence, which might be important in a wind turbine application. Are there any other questions about the technical part? Okay, so then I will talk a little bit, as I promised to Sid, about this effort that we have going on at Iowa State called WESEP, Wind Energy Science, Engineering and Policy. So we recently obtained a funds from the National Science Foundation, the IGERT program, 3.1 million over 5 years, to create actually a new PhD degree. So the students here will get a degree in wind. They will not get a degree in electrical engineering or mechanical. So that's the main idea. And we have 5 thrust areas, 5 research thrusts. We have aerodynamics and wind resource. We have wind energy conversion system and grid operations, which is where I mostly belong. We have manufacturing, construction, and supply chain people, turbine reliability and health monitoring, and also we have economics, policy, and public perception, because we think this is an important piece of the puzzle for wind energy, how to get acceptance from the public and so on. So you can see here all the different departments that are involved. It's across campus and across college, actually. We have different colleges, a lot of people involved. Sociology, economics, statistics, journalism, and so on. Not only engineering, agronomy. And what was our motivation for writing this? Maybe you know this stuff. Wind has been growing very, very fast. It's actually second in growth in terms of new capacity. Number 1 is natural gas, because it's very cheap lately. So we're after natural gas in terms of growth, about annual growth, I think, on the order of 35, 38%, versus something like 40%, 43% for natural gas. New capacity, I mean, new things built. We're second, for us, Iowa, we're second in the nation in installed wind energy capacity. And we're actually second in the nation in terms of how much of our energy we get from wind. Do you know what that number is for us, for Iowa? It's close to 19%. 19 of our energy comes from wind right now on an annual basis. So Denmark, which is touted as the example of high wind energy penetration, is about 20%, right? Or so.
About 26.
26. So we're the Denmark of United States. Number 1 is actually South Dakota with a little higher percentage than us. They just passed us this year. We believe that wind will keep growing, of course, that's our motivation. And we also believe that there's a lot to do in terms of wind turbine technology. Who did I hear say this recently? That the wind turbines we have now look like the cars we had in the 60s. You know, you went through the car wash and you didn't know if the car was going to start after you exited the car wash. This person was working in wind for many years, and he said that this is his impression of current state of the art in wind turbine technology in terms of reliability. They break out a lot very often. You got wiring, you got little things that cost you a lot of time, like the wiring is wrong where you connect the turbine to the communication system. It's very complicated panel, a lot of wires around, you know, things like that. Not only gearboxes and stuff like that failing, but simple stuff. So we believe, of course, that wind is highly interdisciplinary. That's why we have all these people collaborating. And it's consistent with our university mission as a land-grant university and our strategic plan. And there was a report by DOE that said, you know, we're behind in terms of how many advanced degrees we generate every year for wind compared to Europe. We're behind. And we got good industrial support from wind turbine manufacturers, from component suppliers, utilities, and also national labs. NREL is also involved in this. I don't know who in NREL personally, because I'm not the principal investigator here. But we have a lot of industrial support. How is that going to work now? Let me explain to you in a little more detail. So if you enter the program, there's a couple of courses that everybody needs to take, regardless of what their specialization is going to be. And then you will take some courses in your in your main areas of research. You also have to take policy courses, for example, in economics and policy and science, and political science and stuff like that. And then some specialization. The interesting thing here is this part, which for NSF, this is the interesting one. What you do as other stuff that kind of make it more interesting. Cognitive approaches and stuff like that. So we have this thing called the Real-Time Research Collaborative. No. What is that? Let's see. So this real-time research collaborative is some kind of weekly thing that the students will have to take throughout their lives as students. And what they will do is do some kind of mini research cycle every semester together with other people. So they will start a topic, write the proposal, research it, write some kind of white paper. It might not lead to groundbreaking research all the time. Okay, if I put you guys together, let's say you're the students here and you get together, write a topic and do some research. It might not be a groundbreaking thing, but at least it will get you guys talking to each other and learning from each other and, you know, exchanging ideas. So maybe something will come out. At the least it will keep you talking, which is an important part of our objective there. And the other thing that we're trying to do is we're trying to understand how different faculty and students think. So how do you come up with new ideas and research ideas? And let's see if we can observe these differences and, you know, write something about those things. And also to create some kind of template so that as a student, okay, you have different ways to do research. Here they are, and pick the one that best fits you. And that might be helpful because we see that, you know, as a new PhD student, you need to do research. What does that mean? So people do research in different ways. So this might be a way to help, you know, students learn something, you know, how to do research. And the other salient point that I would like to mention is that every student will have an industry internship. Maybe we'll send them to Denmark or I don't know where. Oh, this is the second one. Denmark is the second part, that the international experience also. So we have industry, let's say you go to GE or Vestas here in the United States, or MISO, or I don't know where, NREL, and then you will also go to Spain or Germany. So that's all I had for today. This is part of my research group, and some of the... This is at the Japanese steakhouse, so because this guy graduated, so we were celebrating. But this is the guy that did the... Actually, this is Nick, this is Hao. These are the two guys that did the Vienna work for me. So thank you for your attention. And you have any questions? I'd be glad to take them. We're a little bit over time. But yes, sir.
I just have a small comment to make. Your emphasis on increase of efficiency by even 1 or 2%. I totally agree with you. It takes a lot of effort.
Thank you.
And just a small question. How much time would it take for this technology to get commercial?
Oof. I don't know. You know, I think we're the first ones that actually did this in hardware. And so it's just a prototype now. It's just sitting on a table like that with a 200-watt machine. I think it's you can do it in kilowatt and megawatt level. We actually did this in simulation. We picked out all the components that you need, you know, the IGBTs. These things exist now. You just need to put them together, you know, package them correctly. So I suppose if GE, let's say, sees this paper and wants to implement it, it's doable. It's not science fiction, you know. Could take a year or two, but I don't know if they want to do it, you know. Did I answer your question?
But still, can you give a number to the time frame for which it finds application on the new installation?
The application is there. We are doing this already, you know, the permanent magnet generator. So you just take one box out, replace it with this box. The application is there. You just need to do it in a megawatt level scale. And there will probably be other issues that you will need to solve as you try to do that, which I cannot forecast at the moment. But
Any other questions for Professor Aliprantis?
anything from online, or I don't know. Did anybody log in?
No, I think the online folks have just left.
Okay. So thank you for your attention.
Thanks, Ben. So this ends our cruise seminar series for this semester. We will be posting new information about what's going to happen in fall. Perhaps not at CSU. It will be at one of the other crew universities. I want to take the time to thank Sojus for co-sponsoring this. And one smart grid, information and science and technology in smart grid. That's the topic of the research retreat that's going to begin in about 55 minutes at the Cherokee Room at Lowry Student Center. So, Dan, you had a comment?
The next crew event will be the symposium in August, probably the week of the 17th of August.
So you're welcome to attend that. Please watch the information on crew.colorado.edu. Okay, thank you.
Thanks. Thank you very much indeed. I know you need to stop the stuff. I don't know if it's still running.